talk about the evolution of our understanding. I mean, how we understand the dynamics of the North Indian Ocean. That includes the equatorial part. I'm going to try to step you through about 50 to 70 years of history with a few critical slides. At the end, I hope there'll be more questions than I have answers. So it's broken into 4 modules. In the first one, I look at the observed circulation and the theoretical explanation for the global circulation, not the North Indian Ocean. Module 2 looks at the largely linear theoretical framework we have used to explain what we see in the North Indian Ocean. Module 3 looks at the effects of nonlinearity, and Module 4 looks at the implications for prediction and insight, both of which are of interest. So the observed circulation. Now this is a map not very different from what Pai picked up when he was cast adrift of the Philippines. What you see here, if you look at the global circulation, except the North Indian Ocean, is gyres. The most famous of which is in the Atlantic, and this is an intense boundary current on the western side. It's called the western boundary current. Here it's the Gulf Stream, and of Japan it's the Kuroshio. So you have semi-permanent subtropical gyres. The central latitude would be around just south of California perhaps, and there are intense western boundary currents. The Gulf Stream, for example, carries about 100 million cubic meters per second. So that's the kind of transport we are talking about, and they play a very important role in our climate system. Now, how do we study this? It's basically fluid dynamics as applied to geophysical flows. The scales are very different. If you consider the ocean to be a tank of depth d and length l, d is of the order of a few kilometers, about 5 km, and the length l would be about half the globe. That's the Pacific. So you're talking of something like 15,000-20,000 kilometers. So if I were to represent the ocean basin by the length of this line, it's to scale. The depth of the ocean is the thickness of that line. So it's a very different kind of flow that we are looking at compared to what we see in an IC engine or the flow over an airplane wing. It's a thin fluid, it's a flow on a sphere, and the sphere rotates. We are sitting on that sphere. We are making all our measurements with respect to this non-inertial frame of reference, and we want all our answers with respect to that. I want, for example, the wind relative to the rotating Earth. So I don't have a choice. The Coriolis force is a necessary pseudo force. I have to account for it. And it has consequences, both of them. Rotation and sphericity, I'm not going to bother about stratification. So here what you have is a slab. This is the wind blowing on the surface. So if wind blows on the surface, you expect the current to go downwind. But that's not what happens in the surface of the ocean. The current is directed at right angles to the wind. Because the moment the wind starts moving the water, the Coriolis force sets in. It comes into action only when there is motion. The Coriolis force sets in, the wind balances the Coriolis force, and you have a flow at right angles. So if I have the wind blowing this way, the current goes at right angles to the wind in the northern hemisphere. Now this is called Ekman flow. This is one bit of jargon I will use a bit as we go along. The other consequence is if you look at a tilt of the sea surface. So you have high pressure on this side, low pressure on this side. As you expect, the current starts flowing down the pressure gradient, but then the Coriolis force sets in and the current goes into the wall. So again, it's at right angles. If this seems surprising, just imagine what you see in a cyclone. The low pressure in the center and the flow is around it. So it's not something we are not used to. This is called geostrophy. This is the other thing that's of interest. So you have Ekman flow, where wind stress balances the Coriolis force, and you have geostrophic flow, where the Coriolis force is balanced by the pressure gradient. Now this leads to some remarkable consequences. This is steady state. But if you look at time-dependent circulation, you can do a full course in mechanical or aerospace engineering without encountering waves, except shock waves. But that's not true of the oceans or the atmosphere. Oscillations dominate. So you are looking at waves from word go. So this is a summary of the global ocean. You have these gyres. You have a very thin fluid. you're looking at sphericity and rotation. And you have these subtropical gyres, you have intense western boundary currents. The explanation for why you see this circulation in 5 basins, North and South Atlantic, North and South Pacific, and the South Indian Ocean, came in just 5 years following World War II. 3 remarkable papers, Sverdrup, Stommel, and Monk. And these were steady state solutions because these gyres exist throughout the year. They were steady state solutions, and what you see is westerly winds in the mid latitudes here and easterly trades coming towards the equator. So that's an anticyclone. You are putting in angular momentum, and that's what leads to these gyres. Why do you have the western boundary currents not at the eastern end? You have them at the western boundary because of the directionality introduced by the Coriolis acceleration. It goes from negative maximum at the South Pole to 0 at the equator to a positive maximum at the North Pole. So there is a directionality, and that shifts the boundary current to the west. Now these were steady state theories. When the Challenger expedition mapped the oceans in the 1880s, they bypassed the North Indian Ocean because it was too small to be looked at. Here you have reversing winds, and that was the inspiration for the International Indian Ocean Expedition in the 1960s. It was a remarkable international program with a very large number of countries participating. So you have the winds here in January, the northeasterlies and the southwesterlies in July. That sets up a reversing circulation. So the question is, how do you look at the circulation and what exactly do you see? Now in the short talk, I need to focus. So what I'm going to do is look at just the circulation of the coasts of India. But as we shall see in the second module, to explain even what I see of Goa, I need to simulate the entire basin. So my institute was set up following the IOE and the liberation of Goa in 1960s. What I look at are the results of some cruises in the Indian EZ from 1987 to 1994. And they were carried out by my mentor and academy fellow Satish Shetty and his colleagues. So they were very systematic hydrographic observations. There were 8 cruises spread over 8 years, and they inspired theoretical studies. So finally you had a set of cruises that mapped the circulation and told you what's happening to the currents of the coasts of India. And that led to papers that could use models to simulate these observations. So what happens along the west coast of India? Now you look at these winds, they reverse with season. But there is an interesting catch here. What is of interest to us is the alongshore wind. Because what happens is the following. Suppose this is a coast. This wall is a coast, and I have a wind blowing away from me. Okay, so it is with the coast on its left. What happens is you have Ekman flow, it moves the water out. So the thermocline or the isotherms come up and the sea level drops. Once the sea level drops, you have a pressure gradient with high pressure to my right, that is offshore, and by geostrophy a current sets in downwind. So that's what happens if you have an alongshore wind. If you have a cross-shore wind, on the other hand, it barely sets up a longshore current. So the direction of the wind matters. Off the west coast of India, the wind is mostly directed normal to the coast. So if you look at the component along the coast, it is equatorward throughout the year. The West India Coastal Current, or WICC, flows with the wind, favoring upwelling during July, during the summer monsoon, but during the winter monsoon it flows into the wind. So this is something we would like to explain. Why do you have the current flowing into the wind? It's more easy to understand why the current flows with the wind. That's the normal expectation. Off the east coast, the geography is such that the southwesterlies are almost along. So most of the wind, though it is weaker than in the Arabian Sea, goes into driving a strong current. But curiously, it is during March, April, when the winds are at their weakest, that you have a strong boundary current of the east coast. Now, these are practical implications. If you are drilling for oil in the KG basin, you need to know what the currents are and what the winds are, because both move your platform. You are sitting on sea surface, which is not exactly stable, and you are drilling at the end of about half a kilometer. That's where your drill bit is. So the stabler your platform, the better your chances of drilling. By July, when the wind picks up, the current collapses. So what explains what we are seeing? Now there are questions that I've listed, but I'm going to look at just one of them. Why does the West India coastal current flow into the wind during the winter monsoon? The basic theory is contained in two papers by Taro Matsuno and James Lighthill, and a PhD thesis unpublished, Dennis Moore, 1968, all of them dating back to the 1960s. Matsuno identified the equatorially trapped waves. These are based on the Hermite functions. So these are the dispersion curves of the waves that you get on the equatorial beta plane. Lighthill recognized that there are waves called Rossby waves which propagate westward, and they propagate faster near the equator. If you go to the latitude of Los Angeles, you will see it going at 1 centimeter per second across the Pacific, which means it's going to take about a decade to go from the American west coast of California to Japan. If you come to Kochi, it's 10 centimeters per second. So you can have the Rossby wave going to Somalia within the season. At the equator, it's about 60 centimeters per second. So there's a huge difference between what you see in the mid-latitudes, where it's very slow, and what you see at the equator. This is what Lighthill showed. Dennis Moore's thesis showed how to reflect what are called equatorial Kellen waves. They go eastward. I'll come to that later, at an eastern boundary. So, okay, now here you have a rectangular basin. This is an analytic solution from Julian McCreary, his PhD thesis. What you have here is a rectangular basin. This is in kilometers. And you have a patch of winds restricted to just this part. So you have east-west winds, so they are directed this way, and they decay away from the equator. So you have a Gaussian that decays away from the equator, and again it decays as you go towards this edge. So it's basically restricted to this patch. The response, however, is not restricted to that patch. The waves that are generated, they take the signal created by this wind patch eastward. That's called a Kellen wave, and it goes along the equator at about 2 meters per second. So in a few months, it's at the other end of the Pacific. It reflects as a Rossby wave. Now look at this curve, this parabolic shape. The speed of the Rossby wave goes as roughly 1 by y squared, where y is the distance from the equator. So you have a high speed as over here at the equator, and very slow once you're away from it. So that's why it takes about 10 years to go across the Pacific at Los Angeles, while it's going to do that in a matter of months at the equator. But the reflection is not restricted to just the Rossby wave being produced here. You see a coastal Kellen wave also going poleward on both sides. So these signals can be tracked to Alaska and to Chile. So there is actually a paper in Nature in '93 by Jacobs et al. They used the then available Geosat altimeter to track the impact of the 1982 El Nino, which was the biggest on record till right across the Pacific. So you could see this equatorial Kellen wave and the coastal Kellen wave. This is over within months. But then the coastal Kellen wave pinches off the west coast of the US and then moves right across the basin. 10 years later, it is seen affecting the climate of Japan, the weather of Japan. So that's a kind of memory that you have. Now, this is called remote forcing. I have winds only in this patch, but it affects a much wider expanse of the Pacific. In fact, practically the entire Pacific if you wait long enough. So why does the West India coastal current flow poleward during winter? The first explanations that came invoked salinity. So you have low salinity here, high salinity here. This is the Bay of Bengal with a lot of rivers and a lot of rainfall, a lot of evaporation, and the Indus is almost completely dammed. So there's very little here. So this kind of salinity gradient you don't get anywhere in the world oceans over this kind of distance, except at the mouths of rivers, but they are highly localized. Such a systematic gradient you don't find anywhere else. So the first theories looked at the low salinity here versus the high salinity here and showed that you could actually drive a current into the wind. But if you look at purely dynamical models, these don't have any horizontal variation of temperature or salinity. They produce the current going into the wind in winter. And you need the pressure gradient. You have a high sea level here. The colors show you sea level. So you have high sea level red, and blue is low sea level. So you have higher pressure here, lower pressure here, and you drive a current into the wind. What produces these pressure gradients? It's not salinity. We don't have salinity in this model. We don't even have horizontal variations of temperature. It's coming from this Kelvin and Rossby waves. So you can actually show that by splitting the response. This is a simulation with only west coast winds. You see a response, but it is weak. This is the full response, and this is what you get if you have only west coast winds. That's because the wind is strong, but it is almost entirely blowing into the coast. You have a very weak longshore component. While the east coast wind is just an accident of geography. You have southwesterlies, and you have a coast that is perfectly oriented to put almost the entire wind alongshore. So you have a strong response of Kerala coming from the east coast winds. This is a simulation with only east coast winds. So what happens is you're generating Kelvin waves that go around here and then radiate off as Rossby waves. So remote forcing from the Indian east coast is important for the seasonal cycle of the West India coastal current. So if you're interested in explaining what happens here off Goa, you need to simulate the entire basin. And the problem is it is not restricted just to very large scale systems. Even if your measurements are at something like 10 to 20 meters water column depth, which is where environmental impact assessments are typically conducted, you're looking at the impact of effluent pipelines, the result is the same. So you are talking of a system which has a very large scale, even if you are looking at a very local problem. The simplest model, you just sum the Hermite functions. These are the basis functions for the equatorial beta plane. Now, this is the kind of picture that Chettier brought back when I first came to NIO in 95. I mean, these were on transparencies. The older people here would know them. 12 transparencies, one for each month and global. But even in a global picture, what was striking is this sea level signal that moves off the west coast of India. It's very striking, even in a global transparency, which is just A4 size. Now, this was the first time, this was around 93, 94, that oceanographers could look at a near synoptic view. The repeat cycle is 10 days, but it is as good as synoptic for us. In those days, the processing techniques could give you about a monthly picture at a coarse resolution of about half to 1 degree. Today, they do much better. So how do we explain the observed circulation? You have a waveguide which is leaky. The red is the coastal waveguide, and the blue is the equatorial waveguide, and energy leaks from one into the other. So if I want to simulate the current of just Goa, I need to simulate this entire basin. That is the catch. And that's because remote forcing is important. You produce a signal here, after some time it has an impact somewhere else. And the nature of the waves depends on what the system permits. So that's module 2. This was entirely linear stuff. But we know that fluid flow is nonlinear. So what happens when you start looking at nonlinear effects? This is an example of nonlinear dynamics. This is the coast of Oman. You have the southwesterly winds during the summer monsoon blowing this way. So what do you expect is smooth Ekman drift offshore. That's linear theory, classical linear theory. But that's not what you get. This is a chlorophyll map from satellite. And what you see is that the Ekman flow is not smooth offshore. It's in fact concentrated in squirts and jets that are associated with these capes. If you take a high resolution general circulation model, this is at the resolution of about 5 km, you can reproduce that kind of a system. But you will never get this with a linear model. So there is a nonlinearity here that needs to be accounted for. General circulation model basically divides the ocean into stacks in the horizontal and vertical and solves the primitive equations. They are nonlinear. And these are solved in finite difference form even today. So what is a nonlinear system and what is a linear system for those who are not familiar with that? Suppose you have a black box here. That's our system. And you have inputs I1 and I2 giving you outputs O1 and O2. So I push I1 or I2 in and I get O1 or O2 out. Now if I put in the input I1 plus I2, a linear system will give me O1 plus O2. That's by definition a linear system. In a nonlinear system, you're not going to get O1 plus O2. What it implies is that the principle of superposition, which we learned in school in physics, is valid for a linear system. It's not true for a nonlinear system. Now this is the way the derivative looks for any property S. You can have a local change with respect to time and a change that depends on motion. So let's just look at it quickly. Suppose you have a constant temperature in this room, but you allow for spatial variation. I mean, you will find it is colder near the AC vent than it is away from it. So you have a constant temperature not changing in time, in that if I put a probe at any location in the room, I'm not going to see a change in time. But suppose you have a flow of air and it's going from some temperature T1 to a temperature T2. By the time the parcel goes from here to there, its temperature has to change from T1 to T2. Now that change comes because of this multiple of the speed with respect to the directional derivative. Okay, so this is called advection. So you can change the temperature either locally by, say, fluxes, SE fluxes or whatever, and you can change the temperature simply by advecting a parcel. This is nonlinearity, and it's fundamental to all fluid flows. Nonlinearity also happens to be an essential property of what is called complex systems. With complex systems, you get self-organization into patterns. You just look at any weather forecast, you're going to see cloud patterns. Massive cloud patterns organized on a variety of scales. You start looking deeper into that, you will see more patterns. So there is self-organization into patterns. There is chaotic behavior. I'll look at chaos briefly. There's fat-tailed behavior. You get many more extremes than you would expect from linear theory. There is emergence, which is a consequence of nonlinear interaction. These are properties that emerge as a consequence of nonlinearity. Now these complex physical systems are studied using partial differential equations. There's a fairly well-established body of mathematical theory for that. The problem starts when you start looking at systems that are not amenable to that tool. If you look, for example, at certain aspects of ecosystems or stock markets, because of adaptive interaction, the system can adapt, and then the theory of partial differential equations breaks down. I'll look at chaos and emergence very briefly. So these are the three equations solved by Edward Lorenz in his 1963 paper. They represent classic convection as in the atmosphere, heated from below and cooled at the top. Very simple equations, but they gave rise to this kind of behavior in phase space. Now, the system is bounded. Your variables don't blow up in time. But there is a limit to what you can predict. The horizon is limited. In the atmosphere, for example, you can't make a sensible prediction beyond about 7 days. So you will not find a weather forecasting model that goes beyond that. So this is chaos. You see it in the oceans. My colleagues launched 3 drifters. These are buoys that you just throw out into the sea and they drift. They are Lagrangians, and you can track them using satellites. On 29 November 2016, out here, this is Gujarat, so this is the domain of the West India coastal current. They just dropped them off, and these are just thrown out within minutes. So that's instantaneous as far as we are concerned. They went together for about a week, but then a few months later, they were found in 3 different parts of the Arabian Sea. So that is something you cannot ignore. And this has practical applications. With COVID, we have forgotten one of the most remarkable disasters in aviation history, MH370. It disappeared on 8th of March 2014. I had a difficult time explaining to my wife why in this age, 2014 was bad enough, but in 2023 it's even worse. Why you can't find the debris, why you can't find out where it went down. So this is the rough arc. There was only one sensor working in the engine, so it's a scalar. So you can't pin down where it was, but you can pin down a rough arc where it might have gone down. A few months later, off Reunion Island, they found a wing part. So that is the South Equatorial Current, which is the northern arm of the subtropical gyre in the South Indian Ocean. That's classic linear theory. But these are the drifter trajectories from 1985 to 2015. This is chaos. It tells you why you can't find the place, why you can't find the plane. It's a huge area. It looks small out here, but if you look at the distances covered and it's 5 kilometers down, it's impossible task. It's worse than looking for a needle in a haystack. I really felt sorry for those hydrographers who were sent out on this job. They knew they were guaranteed to fail. Yet there was no choice. They spent months out there at sea. I mean, every day you wake up, you go out, you know you're guaranteed failure. There's no hope, but you still have to do it. Okay, that was chaos. These are propagating waves that we saw. Now you can see them at intraseasonal periods, that is within a season. You can see them at the seasonal time scale, which is the most dominant cycle in the North Indian Ocean. You can even see them at interannual periods. So these Rossby waves that pinch off Kerala or off the equator here and just go westward, they exist at all these time scales. So this is a map, a fast Fourier transform, showing you the amplitude at a period around 3 years. So it's an interannual band. It's a period that you would associate with probably El Nino. Not quite, but it is a rough band. What it shows you is the amplitude of the 50. So red is where there is high amplitude or high variability, and blue is where you have low variability. So this is a logarithmic scale, so every 1 unit here is a factor of 2. So between this blue and red, there's a factor of about 100. Now you would expect that if you generate a Rossby wave out here that has such a high amplitude, you should see its impact right across the basin. The question is, why don't you see it? There are regions here where nothing seems to happen. It's just static. You can use a very simple linear model to simulate this. You can actually get an analytic solution if you replace India by a knife edge. You can do it with paper and pen. And you produce practically this observation. But look at one aspect of the linear simulation. It's smooth, as you would expect for a linear system. And of Oman, the linear model produces a very smooth minimum. In the observations, you have blobs. You have broken patches. If you run an oceanic general circulation model, fully nonlinear, primitive equations, at a reasonable resolution, you get those blobs. I mean, you run it at an even higher resolution than down here, you're going to see much more cleaner comparison with observations. So this is the impact of, this is emergence. And why is it happening? Because of Oman, you don't see that smooth Ekman drift that the linear model picks. You are seeing these kind of squirts and jets that you get in a nonlinear system. But it is the instability of this linear current along the coast of Oman that is producing these blobs. So the current goes unstable, and it goes unstable producing the squirts wherever you have these capes. But if you take a linear system, the capes basically disappear as small perturbations, and you get a smooth flow offshore, producing those kind of minima. So this is emergence. This is a property that arises as a consequence of nonlinearity. So module 4 looks at the implications for two things that are of interest: prediction and insight. This is insight. It tells you why it happens. There is this Rossby wave, it does go across, but in these regions there is a local forcing that cancels it. And the Rossby wave is linear, it re-emerges at the other end of this local forcing patch. You see its effect again. So with this model, I can understand why we are seeing what we are seeing. This is simulation. This is accurate. I can't get that kind of thing with the linear model. But if I were to run just this 5 km resolution GCM, I would not have any idea of what's actually going on. So you have simulation and you have insight, and the two need not go together. There is no question of why you want prediction. That's obvious. The chlorophyll filaments can be simulated fairly well with a high resolution model forced by observed winds. Now in a forecasting system, the only way you achieve reasonable accuracies is by what's called data assimilation. So you look at a typical atmospheric forecasting model, you run it for say a day, then you take in the data that Professor Atmanan spoke about from various sources, land and sea, and you assimilate them into an analysis, and you run what's called either an adjoint operator. When the model runs backward and forward, it tries to assimilate the observations, blending the observations with the model. So you're basically getting a cross between what the model tends to simulate. It drifts away from observations, so you're getting a model state combined with observations. So it's neither model nor observations, it's a cross between the two. And that's the only way you get reasonable accuracies in a forecasting system. And its relevance becomes less and less as you go further into the future. So the chaos that is inherent in such nonlinear and complex systems limits the forecast horizon. In data assimilation, the model is run for some time, and you assimilate data and you rerun it. So every day you see a forecast being updated by the India Met department. Now what do you do when you want to simulate climate? This approach is not viable. You can't assimilate data. There's nothing available to assimilate over 70 years. What you do is throw in scenarios, carbon dioxide, whatever, this scenario or that scenario, and you run it, assuming that that's going to be constant. So you cannot assimilate data when running a model over a season, which is what IMD wants to do, make a seasonal forecast, and it's difficult because it's purely model dependent, or years or decades. Yet forecasts are made, and there are serious practical consequences of any decision made on the basis of these models. So what's the difference between simulation and understanding? Simulation implies capturing as much of the system's complexity as possible. Understanding implies sufficient simplification to capture the essence of the phenomenon. This gap between simulation and understanding was discussed by Isaac Held, an American meteorologist, in an essay in 2005. The practical value of simulations is undoubted. Nobody doubts it. You want to make a prediction. I mean, the stock market reacts to monsoon forecasts. But in today's world, is understanding or insight still important? I'm going to leave you with this question, though I try giving an answer to it. Held notes one practical importance of understanding, comparing models. Now, if you look at any IPCC forecast for any given scenario, you are starting off all the models from the same state, same set of initial conditions. They diverge after some time, and there is a huge spread. You have say 15 models and you have a huge spread in what they say is going to happen 50, 70 years from now. How do you know what is right and what is wrong? So that is one practical importance of understanding, comparing models. You want to know why a model goes wrong when it goes wrong, and you want to know why a model, for that you need to know why it is correct when it is correct. And I recall one statement by the former Pakistan cricket captain Imran Khan. He once said, good teams analyze their failures, great teams analyze their successes. So you want to know what is causing that spread. Which one do you believe? And there are huge practical consequences. Do you buy an electric vehicle or petrol vehicle if you are going to replace your vehicle tomorrow? The problem lies here. Now, climate constitutes a complex physical system. Isaac Held compared climate science with molecular biology, which also deals with complex systems. But he noted one vital difference. There's a complete hierarchy of biological systems, from viruses and bacteria on one end to human beings on the other. You have the entire spectrum available to you. There is no such hierarchy of climate systems. So you have to construct a mental hierarchy of these climate systems if you want to do what biologists have been able to do. Held compared the phenomenal progress in molecular biology over the last few decades with the relatively poorer progress made in climate science. He also noted one more thing. Though biologists have an incredible variety available to them, they still focus on one or two organisms. E. coli, for example, and Drosophila melanogaster. You will find an incredible number of papers on them. Because if you study E. coli and I study E. coli, the results are comparable. So Held said that you actually need some focus. You cannot build, everyone cannot have his own model. You need some consensus. And this consensus is not easy because you have national models, you have geopolitics, a lot of things coming in. So it's not easy to build this consensus. Yet the consequences are global. So you need to build this hierarchy of models, and they are mental constructs, not like what you find in biology. So complex systems, you have this buzzword today, big data and models, and there are two competing views. They are very old. One extreme view is due to Fredkin and perhaps best expressed by Stephen Wolfram of Mathematica. The universe is in essence a simple program. A set of algebraic rules, you just start from some initial condition and let it spin off. And you can generate phenomenal patterns. This is not a cyclone, it's a fractal image of that looks like that. So is this how atmospheric science works? This is not broccoli. This is another fractal image. So does nature 3D print broccoli? So this is one extreme view. And that is what we are kind of heading towards with artificial intelligence. The other extreme view, which perhaps is no longer as strongly prevalent, is due to Clifford Truesdell, who called the computer ruin of science and a threat to mankind. This is a 1984 paper. But you have serious questions with the explosion in computing power and what is called proof. We had a talk some time back where proof is complete. You can probably find mistakes in the proof, but once it is proven, it's finished. You cannot disprove Pythagoras' theorem. You can find better ways to prove it, but you cannot disprove it. It's over. That is the way mathematics works. But here you're talking of proof in a complex system and one which has consequences for humanity, climate science, for example. So how do you deal with this? That's why this problem with proof is why you can take different positions with respect to climate. There are issues with no matter what model you pick up. But this competition is not new. In two articles in 2003 and 2005, Rohan Narasimha looked at the difference equations and accurate astronomical predictions that were made by Indian astronomers, and they astonished a Scottish mathematician called Playfair. He's the one who was taken aback by that. Till Newton and calculus, these predictions were far superior to anything in Europe. What they were doing is using difference equations. They were meeting every few decades, updating coefficients. They had no problems using epicycles. To Aristotle, it caused a lot of fundamental philosophical problems. So they were basically doing some kind of crude data assimilation, but they did not have a model. And they abhorred models, while Aristotle had models. And he had those concentric spheres, spherical spheres, concentric spheres with glasses. It was the marriage of Indo-Arabic algebra and Greek geometry with Descartes and the Newtonian revolution that changed everything. So model building started with that. The question is, in this age of the chip with Moore's law, big data, artificial intelligence, and self-learning neural networks, does the differential equation still matter? I have a serious question here because I have to make a practical judgment. In a limited curriculum, do I still teach the dispersion curves put down by Taro Matsuno? Or do I tell them just forget about it, just learn how to code AI? There are practical consequences, and I'm sure that I'm not alone with this question. So that's an interesting topic for discussion. So it's a question of calculation, as in simulation, versus deduction from axioms of first principles. It's a philosophical problem, and at the same time one with very severe practical consequences. Just go back to Isaac Held. There's a practical, not merely theoretical or academic need for insight. You're projecting into the future with no way to know which of those models is actually going to give you the right thing. None of them succeeds with the current Indian monsoon, for example. And even with respect to something like aerosols, there are diametrically opposite schools of thought. One says that India will benefit, there will be better rains, and the other says no, it's going to be a dry state. So what do you plan for? If you're an agricultural scientist, do you plan for floods or do you plan for, what do you call that, droughts? My own view is take the middle path between the pen and the chip. I don't know how long it will run, and relevant data. The last point here is that we always think in terms of big data today, but earth science is a sparse data problem. If you look at the elements of the earth system as a matrix, there are parts which are very dense, which is where you have satellite data coming in. But there are large parts that are blank, and they contribute equally, if not more, to what you are seeing. So I will not go over this summary. Now these three pictures give you three views of linear versus nonlinear flow. Three measures of linearity. So where you have these purple and blue colors, you have a dominance of linearity. So you can see that in our region, in the tropics, except near the western boundary, it's fairly linear. It's a full toss and open goal. You have to put it away. So that's it. Thanks.
I had a question about taking land masses into consideration in your, because your land masses and the atmospheric conditions of heating and are also then going to drive your wind, which
Correct.
will drive many of the phenomena.
Coupled system.
Sorry?
It's a coupled system.
It's a coupled system. So I was wondering how are land masses taken into this scenario at all, or that's not
It depends
relevant?
on what kind of model you're using. If you're using an ocean model, you take the winds as given. If you're using an atmospheric model, you take the sea surface temperature and the land surface conditions as given. Then there are coupled models. So when I was a student at IISc, they were very bad. This was in early 1990s. Today they are good. And that's what you're seeing in the IPCC reports today. How good they are, you judge by the spread. And you can take any view. So that's why in the US you will still have a strong political debate, because both are plausible. See, what does the model do? It takes a certain view of the phenomenon and puts that into mathematical form and then codes it. In any atmospheric model, the problem comes with processes that are within a grid. So you have your grid nodes. Say you have a 50-kilometer resolution. So every 50 kilometers you have these points where you have your velocities, for example. What's happening within that? And the biggest problem is cumulus parameterization. The cumulus clouds that you see have a length scale of about 10 km. And they are turbulence. The other part of the code, an atmospheric forecasting code that eats up time, is radiation. Line by line calculation of the radiative heat transfer. So in a way, those two problems that Kelvin noted in 1889 are still there with us. It's solved, the black body radiation problem, but radiative heat transfer is a nasty piece. It eats up a lot of computer time. So AI may help there in reducing the computer time. Cumulus parameterization, it's still a mess because you're dealing with turbulence at its core. It's still an unsolved problem.
Shankar, you just said that artificial intelligence might help. I mean, the philosophical problems aside, there are some developments over the last couple of decades on using AI, ML methods such as reservoir computing and so on that actually make it possible to do medium-range predictions in chaotic systems. Have these been used in climate models at all?
I don't know. I won't be able to answer that. But I'll tell you the bigger problem is not which method you use, whether you use AI or don't use AI. The problem is not with method. The problem is the unwillingness to recognize that you are not dealing with a big data problem. You are dealing with a sparse data problem. I don't have a world map here. I'll have to go back to that slide. But if you have some idea of African geography, from the Red Sea, where you have Sudan, for example, and Eritrea, to almost the Atlantic on the other side, there are no radio sound observations. There's civil war and a mess all over the place, over a wide swath of latitude and the entire longitude band between Red Sea and this place. Now you stretch it into West Asia and farther north into Ukraine. Would you be launching radiosonde balloons given the conditions out there in Ukraine and Russia? So huge swaths of places where you could actually make measurements. This is not like the ocean, where you can't make those radiosonde observations. They're out of bounds today. You have either no money or you will probably get shot down.
Excellent question at the end of your very beautiful talk. The question still remains is that since we started in 1980s, late 80s, about the physical oceanography cruises in the Bay of Bengal and the Arabian Sea, which I'm familiar with that, all those cruises. And so down the line in now 2020s, what is the new information which we have achieved in terms of the dynamics of the North Indian Ocean?
Okay,
Which we can say that this is what we were not knowing 30 years ago, 40 years ago, and this is what we know today. So that our prediction or understanding of the biogeochemistry coupled system, as well as the physical exchange between even you can say within the ocean or the ALC exchange.
okay. I have those slides, but
Just a one line answer which I would like to.
for the last 15 years, we've been running a program making direct current measurements. Now, we have enough data now to ask one very simple question. On a given day, let's say 5 November 2023, in what direction do you expect the West India coastal current to flow? And the answer is it could go in either direction. It is not the picture you got from hydrography. Intraseason. No, wait, let me finish. You go to the east coast of India. The old observations, the hydrographic observations of Shetty et al., they are still valid because the seasonal cycle dominates. So there is a greater probability that I will get the current in the expected direction based on my understanding of a seasonal cycle. On the west coast, it could go practically in either direction because intraseasonal variability dominates. Now, what this implies for biogeochemistry is a different business altogether.